Welcome back to AlgoStock. If you haven't seen our previous video on decision trees, I highly recommend giving it a watch. In that video, we explored how a single detective, a decision tree, uses clues to make predictions. Understanding how decision trees work is crucial because today, we're taking things up a notch with a more advanced team of detectives, the Random Forest. In our detective story, you're running a lemonade stand and want to predict how much lemonade you'll sell on any given day. In the last video, we used clues like temperature, whether it's a weekend, and whether there's an event. But in real-life cases, the clues are rarely that simple. So this time, we've expanded our dataset with even more suspects. Now, alongside our original suspects, we're also considering if it's a holiday, how much money we're spending on advertisements, the discounts we're offering, and even if it's raining. Each of these factors might influence our sales, and relying on just one decision tree may lead to unreliable predictions. This is where Random Forest steps in, a collection of multiple decision trees, each working independently to get to the bottom of this case. By pooling their insights, Random Forest can handle the complexity and deliver a more reliable prediction. Alright, let's take a closer look at our expanded dataset. We now have 40 observations, each one representing a unique scenario for our lemonade stand. Here's what the dataset includes. There's a general upward trend in sales with increasing temperature, suggesting higher temperatures tend to boost sales. Sales versus weekends. Sales are notably higher on weekends, reflecting consumer behavior favoring more purchases during weekends. Sales versus event. Events have a clear positive effect on sales, with a visible jump when an event is present. Similarly, we can dive deep into each of the features to see how they individually affect lemonade sales. For instance, we could visualize how rainy days impact sales or how advertising spend influences customer turnout. But don't worry, I won't bore you with every single analysis right now. Just remember that every feature offers a clue, and our Random Forest detectives will explore them all to find the best patterns. Each clue counts, and the forest will handle the heavy lifting for us. So, why do we need Random Forest regressors when we already have decision trees? Decision tree can get swayed by some noisy clues outliers or overfit to a specific part of the case. But what if we assembled a whole team of detectives? Each detective tackles the case from a slightly different angle, looking at various combinations of suspects and clues. They create their own decision trees, all slightly different, and once they've each reached a conclusion, they work together, averaging their answers to make sure we get the most accurate and balanced result. This is the power of Random Forest: collaboration, multiple perspectives, and ultimately, a much better prediction. Alright, let's dive into building our Random Forest. One important decision we have to make is, how many detectives, how many trees, do we want in our forest? The default choice is 100 trees, which would give our detective a huge team of junior detectives working together. But remember, we're just dealing with 40 data points here, a pretty small case study. So, to keep things simple and focused, I'm giving our lead detective a smaller team, just 5 junior detectives. That's right, we'll create a Random Forest with only 5 trees. To make sure our team of junior detectives doesn't all come to the exact same conclusions, Random Forest uses a clever trick called bootstrap sampling. Even though we have a dataset of 40 observations, to make it easier to understand the concept of bootstrapping, let's simplify things and imagine we're only dealing with 6 clues. Each junior detective doesn't get the full set of clues. Instead, they receive a random subset. On average, about 63% of the samples they get will be unique, while the remaining will be duplicates. Now, to show how bootstrapping works with our full dataset of 40 observations, let's look at a visual example. Imagine we're examining the event versus sales relationship graph with all 40 points visible. When we assign data to our first junior detective, they only get a random selection of 27 unique observations. To complete the dataset for analysis, the remaining 13 points are randomly chosen from this initial selection of 27, meaning some clues data points will be duplicated. This duplication happens randomly, and it's possible for some points to appear multiple times in the final set. This way, each detective gets a slightly different view of the case, ensuring a variety of perspectives while still keeping core patterns in focus. Each detective works like decision tree algorithm looking for the best threshold that minimizes the MSE each split. It does this using all 40 rows in the bootstrap sample, including any duplicates. If a row appears multiple times, it has more influence, affecting both the target variable like sales and the feature values like temperature. For example, if row 3 is repeated in the bootstrap dataset, the tree includes it in the MSE calculation for potential splits, effectively weighting that row more heavily. In summary, while only 27 rows might be unique, the repeated ones still impact the split decisions since they are part of the dataset. To understand how each tree is constructed step by step, make sure to check out my previous video, which goes into detail about decision trees. The link is available in the description below. In our random forest setup, the detective agency Random Forest gives some specific instructions to each of its 5 junior detectives' decision trees. Here's what these instructions mean. Max_depth equals 3. What it means: this sets a limit on how many times each detective can split during their investigation. It controls how deep each tree can go in looking at the clues. A max_depth of 3 means that each detective can split the data a maximum of 3 times. Why it's important? Limiting the depth helps prevent overfitting by stopping the detective from making the investigation too detailed. The detective stops investigating after 3 layers, which ensures they don't get overly precise and create a story that fits just the training clues perfectly but fails on new cases. Min_samples_split equals 7. What it means: this sets the minimum number of clues data points required in a group to allow a split. If a detective has a group with fewer than 7 samples, they won't split it any further. Why it's important? It's a way to prevent overly detailed investigations by ensuring that there's enough data in each split to make a reliable decision. This stops the tree from splitting groups that are too small to provide meaningful insights. Max_features equals 3. What it means: this limits the number of suspects features that each detective can examine at each split. A value of max_features equals 3 means that, at each split, the detective randomly picks up to 3 suspects from the total pool of suspects features to consider. Important note: this does not mean that the detective only gets 3 suspects for the entire tree-making process. Instead, at every split decision, the detective randomly selects a subset of suspects, maximum 3 from all available suspects. How Detective 1 works the case. With the bootstrap sample, now that we have our parameters set for the random forest, let's dive into how Detective 1 approaches the case using the bootstrap sample. Remember, this detective operates under the guidance of the random forest instructions we've established. Detective 1 to decide which features to analyze for making splits. With max_features equals 3, the detective randomly picks maximum of 3 suspects from the pool of all available features. Suppose Detective 1 randomly selects temperature, event, and its spend to consider for their first split. Considering all the possible splits across these 3 features, Detective selects the split which gives minimum weight or MSE. In this case, it is given by the split at 28.5 to 3 by temperature. Once the first split is decided, Detective 1 continues the investigation within the left and right groups formed from that split, applying the same logic. Moving to the left node, though it is possible to split this node, but Random Forest Agency has given the instructions to not split the node with samples less than 7. Hence, this node is turned into leaf. So, if temperature is less than 28.5 to 3, this detective will simply predict the sale value to be 73.889. As for the right node, there are 21 samples present. It is time to again select maximum of 3 suspects from the pool. Suppose this time Detective selects event, weekend and rain. Repeating the same process to hunt for the lowest weighted MSE, Detective found that splitting the data based on event would be most accurate. The same process is followed again to grow the tree further. Upon reaching at this depth, Detective has to stop since, again, Random Forest Agency allowed Detective to go only till depth value of 3. In the similar manner, as Detective 1 has made its tree to solve the case, other detectives work hard with the bootstrap samples given to them to come up with their own tree. How it predicts. Suppose we have a new set of clue and we seek Random Forest Agency's help to predict the sales we can expect today. Random Forest calls its first detective and asks for the prediction. Looking at the first node, it notices that the temperature is less than 28.5 to 3, hence the predicted sales value for today is 73.889. Now Random Forest calls second detective and asks for its analysis. And looking at today's temperature, this detective predicts the sale to be 78.019. Now calling the third detective. This detective first looks at the event, and since there is not event, detective moves to the next node looking at the temperature, which is less than 34.703. Detective moves further down to look at the discount value. Since today's discount is less than 14.212, this detective determines the expected sales to be 93.564. Random Forest asks what other two detective thinks in the same way and note down their observations as well. Predictions given by these individual detectives are averaged by the Random Forest to get the final prediction value of the sales to be 84.2744. Pitfalls and misconceptions. Despite its strengths, Random Forest has a few challenges. Overfitting. While less likely than with a single decision tree, random forests can still overfit if not carefully managed, for example, setting the depth of trees to high. Interpretability. It's hard to interpret a random forest because it involves multiple decision trees working together, making it difficult to trace how specific predictions are made. Computation. Building and averaging multiple trees is computationally more expensive than just using a single decision tree, especially with large datasets. Conclusion. Random Forest is a powerful tool for making predictions. By using a team of decision trees and providing them with different clues and suspects, it solves complex cases more accurately than a single detective could. This ensemble approach enhances prediction accuracy and reveals hidden patterns in the data that simpler models might miss. However, this complexity can make the model harder to interpret and increase computation time. Next, we'll explore extra trees, which builds on Random Forest by adding even more randomness to improve speed and performance. Get ready to discover how this unpredictability can lead to sharper insights in machine learning. Until next time, keep investigating the mysteries in your data.